Okay, so we'll just kind of jump in there. I was pretty sure this is where we stopped last time. Okay. One of the things we can appreciate in the nighttime sky is something called the Milky Way. And the Milky Way is looking into the frisbee of stars that we're on. Okay? So when we look at the Milky Way, I think I've said this before, but kind of smack dab in the middle of that Milky Way is the disk of the MW. MW stands for Milky Way, the disk. So above the disk, we have the halo region, and below the disk, we have a halo region. So honestly, kind of those miscellaneous stars that make up the constellations we love, Hercules, Leo, Cassiopeia, those stars that make up those shapes are in the halo region. Okay, so they're little miscellaneous stars. It's kind of neat. So this is kind of cool. This is looking at, we've never been hovering above our galaxy, the Milky Way galaxy, to know it has this spiral shape, but we've seen other galaxies that have this spiral shape, and we can infer, you know, from our position that we are in a spiral galaxy. But this slide kind of emphasizes that throughout the course of a year, we actually are going to see different parts. That band we call the Milky Way, it's going to change. And so let me try to kind of explain it this way. Not drawn to scale. If that is the sun down there, that's just a star that's part of the Milky Way galaxy. All those kind of things that look dusty, those are other stars. So we have all the planets that are orbiting the sun. Let me go ahead, not drawn to scale. Okay, let's make this the Earth. And I'm going to kind of show it going counterclockwise around the sun. If the Earth is right here, can you see where at nighttime we're going to see this part of the Milky Way? Does that make sense? Okay. If the Earth is over here, okay, if the Earth is over here, I know not drawn to scale, right? If the Earth is clear over here, can you see at nighttime we're going to see this part of the Milky Way? Does that make sense? So as we orbit the sun, we get different parts of the Milky Way, or the Milky Way will change. Okay, so remember I said like the moon right now is 7 degrees. That's what Stellarium told us, 7 degrees above the horizon. It was talking, is it always going to be 7 degrees above the horizon? No. It's going to keep rising. Just like the sun rises, the moon's going to rise, the stars rise. And it's kind of nice because, like, that's east, right? All that stuff's going to rise in the east and set in the west. Okay? But where it is on our local sky is going to change. So one way we say on our local sky how an object is like the 11 degrees or the 7 degrees. For instance, this person is pointing to the star, and with regard to the horizon, okay, so she has to put out 2 hands. This looks silly. But one hand's the horizon, one hand's pointing at the star. That angle right there is 60 degrees for that star. Okay, that's what we call the altitude. Okay, and she went ahead and put in direction. So it's 60 degrees. And she went ahead, and there's different ways to say kind of which direction it is. You know, is it south or north or, you know, east or west? Well, one way is just simply to use those words. So it's between east and south, so it's southeast. Well, our local sky, it changes, but we need to be able to kind of point on our local sky to a few other things. Straight overhead on your local sky is called the zenith, okay? So the horizon is basically, you put out your hands and all the way around. You have a horizon, you know, 360 degrees. Coincidentally, or it makes sense then, our zenith is 90 degrees from our horizon. So there is a special line that goes from due south to due north through straight overhead, and that's called your meridian line. So if that's south and that's north, straight overhead, kind of just picture a line. Okay, that's the meridian. Okay. So I was doing this earlier today to kind of judge the distance from the horizon. It's helpful to be able to kind of say 11 degrees or 60 degrees. some sort of thing we always have with us, i.e. our hands, to kind of judge kind of distances. So the deal here is if you extend, if you're normally what people are able to do is if you extend your hand, your finger will cover 1 degree. Cover 1 degree up. Okay? Your fist will cover 10 degrees. Okay, so the moon right now is about 10 degrees on the horizon, and you're like, that might be why we can't see it, because we got trees there. 7 degrees. And then we go up to 20 degrees. Okay, so 20 degrees is about from here to here. Okay, so, for instance then, some kind of common things. The asterism, the Big Dipper, part of Ursa Major. The bowl stars, the end bowl stars, otherwise known as pointer stars, to Polaris, they are about 5 degrees apart. So they would be about a half of a knuckle to knuckle. They're about 5 degrees apart. And here we go. The disk of both the moon and the sun, which is kind of fun, because that's why that's a nice feature. From our perspective, those disks both are about a half a degree. So if you take your finger, about half of that. Okay. And if you're like me, does it seem like the moon is bigger when it's just rising or setting, when the moon is close to the horizon? And if you read about it, it's playing tricks on our mind. So to remove the trickster out of it, try this. When it's rising, put your finger out, see if it's about half of your index finger, and then when it's straight overhead, put your index finger out. Okay? I dare you. Okay. So, degrees. We're used to degrees. You guys, how many degrees are in a circle? 360. But degrees can be broken down into minutes. So there are 60 minutes in a degree. And it says arc minutes, but it's the same thing. 60 minutes in a degree. And there are 60 seconds in a minute. 60 arc seconds. So a degree has that cute little circle, 1 degree. If it's a minute, it has 1 dash. It's kind of like maybe what you're used to. If it's a second, it has 2 dashes. Okay, so I take the math out of it, right? But do you buy this that, I'll just put this whole thing up here. There's a mathematical relationship down here. And it's an equal sign, and it involves multiplication and division. And it basically says that if you're looking at an object, okay, and you know it's how big the angle is, okay, the angle at what we say subtends, okay, and if you know one other 2 pieces of information, if you know the distance to that object, you can get how big that object is, its real size, okay. Or if you know its real size, you can get the distance to that object. Okay, you can go either way with that, just knowing the angle and one of those other 2 pieces of information. Okay, and here's the relationship. Okay, so the sun appears to rise in the east and set in the west. The moon appears to rise in the east and set in the west, if you can find it. Okay, and those things happen because the Earth spins on its axis. So, last we were in here, must have been Wednesday, we talked about something called a celestial sphere. Okay, so I'm counting on you guys remembering that model. And I brought my celestial sphere today, but last night I accidentally broke it. So, it's very old. This is the model, scientific model called the celestial sphere. So what are those yellow dots? This is the sun. Where is the yellow dot? The sun. Yeah, thank you. That's the sun. Very good. And what are those other dots?
Stars.
They're just stars. Exactly. Okay. And what's in the middle? The Earth. Yeah. And that's exactly what we said. That this is called the celestial sphere. Now, are all stars really just the same distance from the Earth like this? But this kind of works. Does it look like they're kind of stuck together in patterns that we can call different constellations? Yeah. How many constellations are there? 88. 88, yep. Very good. Okay. So in this model, like I said Wednesday, and that's really broken up, we can picture the Earth spinning on its axis, okay? And as the Earth spins on its axis, that is why the stars appear to move. Now, we know the stars appear, yeah, and that is actually why the stars appear to move, because we spin on our axis of rotation. So this caption under here says that the Earth spinning in there is going from west to east, and it makes the stars appear to go from east to west. And I'll just kind of show you with the celestial sphere and the Earth in the center what that caption's talking about. So if you focus on this right here, okay, that Earth is spinning, looking down counterclockwise, isn't that right? Okay, and it is going from west to east. So my best way to kind of point out what this figure is trying to talk about is if you pick one of the bands, let's pick this band here in the northern part of the celestial sphere. Look what it's showing you in the front there. It is appearing to go from east to west because of the rotation inside of the Earth. Okay. It's a small thing. All right, diurnal motion. Why does stuff kind of move? But it's not chaotic, thank goodness. Can you imagine if for whatever reason you lived on a planet that the nighttime sky, the stars just kind of said, all right, I'll go wherever I want to go. But they're very ordered. And the sun is very ordered, the moon is very ordered. Okay. So diurnal motion is talking about stuff moving because the Earth is spinning. Okay, and I think I've said this a few times. I'm going to kind of remind you because I have some slides coming up. What's the clock for this? What star is it? Polaris. It is Polaris. Very good. And so the stars will appear to move clockwise or counterclockwise? Counterclockwise. Very good. So it'll appear to go like this. Okay. And if I think I said before, you can make it a bullseye, Polaris, and kind of make circles going out. But eventually you're going to hit the horizon, okay? And then it's going to appear to rise in the east and set in the west. And then actually it will continue till back over there. Well, Polaris, right? We need Polaris for the semester. The bullseye, I said, that actually kind of goes out in all directions and hits the horizon. Okay? Picture that circle hitting the horizon. Anything in that circle is what we call a circumpolar star or a circumpolar constellation. Why? Because even as they go around that circle, they're never going to go below the horizon. They're stuck. Circumpolar means they're always going to be in that circle, in that bullseye. Okay? Which is nice. The Big and Little Dipper fall in our bullseye. Okay? So it's kind of nice. Very nice. So this kind of points out, if you were, let me kind of put all this up here. If you were this little guy right there, do you see him? Isn't he adorable? If you're that person standing there, which looks kind of like, it might be us, because I kind of see Mexico, and it looks like North America. Okay? So you're standing there. We now have tilted the axis of the Earth's rotation. Okay, so now we're like that. The person's zenith is right there. Then the person has horizons going this way and this way. So the light blue is that person's local sky. That light blue is what he can see. So the point here is, can you see where this little star down here that's taking this path, okay, on the celestial sphere, can you see where it's just barely below this person's horizon? He gets other stars, right, thank goodness, but he is never going to see that star. Good luck with that. Okay? And similarly, this star up here, he's always going to get a C. Circumpolar star, and this one down here, he's never going to see. Okay. So, here's the deal. Let's take a road trip, not to ChemLab, but let's go up to the North Pole. Okay, so we're going up to the North Pole. We're going up to the North Pole, and we look straight up at our zenith, so like this polar bear, right? What star is at our zenith?
North Star.
The North Star, very good. Polaris, exactly. Road trip, yep. Because the axis of rotation is going right through us, okay, and Polaris is right up there. Okay, so let's look at Polaris. And let's go ahead and make circles. And so which direction the star is going to go around Polaris? Counterclockwise again, yep. So we make a circle, a bigger circle, and then down at the horizon, a bigger circle. Okay? So if we were to do those star trails, you know, take your camera, open up the shutter, and kind of watch the movement of the stars. Okay? If you're looking in any direction, you're a polar bear. That's why he's just going to seem like that. Star trails are different. Well, maybe even better than that. Let's take a road trip to the equator. Okay, so let's go to the equator. And we're going to look for Polaris. Okay? Where is Polaris if you're at the equator? Exactly. It's like on the horizon. Exactly. Polaris would be right out there. And there is no star in the southern hemisphere that our South Pole points to. Okay? So, but the South Pole would be that way, and the North Pole would be that way. All right, so let's look at Polaris on the horizon, and let's go ahead and make circles. But we can only make semicircles, can't we? Make a little circle, and let's see, oops, I was going clockwise. Make a little circle, make a little circle, a bigger half circle, excuse me, a bigger half circle, a bigger half circle, a bigger half circle. Okay, now we're going due east and west, a big half circle, okay, and then we do the same thing over there. Okay. So that's why what this is saying, if your palm tree is kind of representing what you might see down at the equator, if you are looking either due east or due west, you're going to see the star trails just go. Right? So here's the deal. Do you guys buy this? If you are at the equator, Polaris is there. Do you have any stars that are circumpolar? No. They all just, there's no bullseye there to deal with. Okay. If you're the polar bear, you have the North Pole or Polaris at your zenith. How are you doing for circumpolar stars? They're all circumpolar. So that's kind of what's meant by those things. Well, in our neck of the woods, if we were to kind of do a sky trail, this is 45 degrees latitude, either south or north, and we're about 40, so they would take on an angle like this. And we'll talk more about that. But I want you to remind yourself, if we look at a globe, okay, it's kind of neat because like years ago, we couldn't position ourselves like we do now. Like there's apps for everything. You could get an app to say, what longitude and latitude am I at? And it's like kind of creepy, right? They would tell you the crosshairs of longitude and latitude, your position. But I just want to remind you, when we talk about lines of latitude, we're talking about relative to the equator, lines of latitude, okay? When we talk about lines of longitude, actually, we're talking about these lines, okay, of longitude relative to the prime meridian, okay? So latitude goes from 0 to 90 north, 0 to 90 south. Longitude goes from 0 to 180 east and west. Just to kind of remind you. So I don't know if you have a homework question this semester about this or not. And I'm going to try to convince you. But the way this works is if you share a line of latitude with somebody, like we are, I said, about 40 degrees latitude. Okay, we can go ahead in the northern hemisphere, draw a line in our latitude, and all these locations are going to see the same sky. Not at the same time necessarily, but they'll have the same set of stars up by latitude. And what your author's done to kind of maybe give you a running start at that is take two locations, one in the northern hemisphere, that's the polar bear again on the left. Over here, this is a location in the southern hemisphere. Okay, and just like the convention has been for these figures, kind of that light blue is that person's local sky. So they have different local skies. Why? Because one's at 90 degrees north latitude and one's at 34 degrees south latitude. If you change your latitude, you're going to change your local sky. If you change your longitude, you're going to have the same local sky. When I was kind of going like this at 40 degrees latitude going around, I'm changing my longitude. I'm changing my east-west position. As long as my north-south position is the same sky. All right. So, speaking of different skies, okay, so this is kind of nice. We see the Little Dipper and the Big Dipper in this view. And so folks in the southern hemisphere, especially if you get too far in the southern hemisphere, you're not going to be able to see these stars. But the way this works is you see here, this is 0. This is 2 hours later, 4 hours later, and 6 hours later. Okay? And you can see the Little Dipper kind of swinging around, but Polaris stays put. And similarly, you can see the Big Dipper at 0 hours, 2 hours, 4 hours, and down here, when it's nice and dark again, 6 hours. Okay, it's just kind of showing the motion. Well, what about the southern hemisphere? I told you they don't have a star, okay? But what they have is a constellation. This constellation is another cross. We have the Northern Cross, or Cygnus. Okay, they have a cross. It's called the Southern Cross, and it's smaller, less complicated. So here's their Southern Cross, and even though there's not a star there to kind of show motion around throughout the course of the night, what they do is they take this length and go about 4 times. Isn't that hard? Bless their hearts, their Aussie hearts. Okay, so that's a region of space, no star. Okay, but the stars are going to move around that space. There's one more catch. In the southern hemisphere, like you see, the movement is going to be clockwise. So here we go, clockwise. So at 0 time, here's the Southern Cross, 2 hours later, 4 hours later, and 6 hours later. So they're going to see things sweep around clockwise. I guess if you were MacGyver, you could like go out, he probably knows all the constellations anyway. But you could go out and watch the movement and get a sense for what's going on, which hemisphere you're in. So, here's where I get to say this very awesome fact. Have you ever seen like old navigation tools and like the pirates, what they used to do? They used to use these, are they sextants? Okay. To actually know which latitude they're at. Here's the deal. If you find Polaris, you draw your arm where the horizon is, you put your other arm where Polaris is, that angle is your latitude. Okay, so Polaris every night should be about 40 degrees for us. Where's Polaris for the polar bear? Very good, up. So you put it the horizon straight up. What angle is that? 90. Okay. Where's Polaris for the equator? Straight out. Exactly. So straight out with the horizon, what angle is that? 0. 0. Okay. So, yeah. So I think that's a good place to stop. And we'll pick up. So this chapter won't be due on Monday. Or wait, no class on Monday. This chapter won't be due on Wednesday. Will not be. But Wednesday we'll get through the chapter, so we'll be due Friday. Okay?